Well, I think it's official. Welcome back, everyone. Well, for today's class, we're going to go over chapter 2, and we probably will get pretty far on this. I'm not completely certain if we'll finish chapter 2. Will depend on just how fast we go, what questions folks ask on it. But just in case we get pretty well through it, I posted the assignment number 2 just a little bit early. The due date is January 24th, but these are always going to be in flux in this class. The due date becomes official the moment we actually complete a chapter. So this due date is definitely official. This one's due today. That's because we finished chapter 1 a week prior. That must have been January, let's see here, January 10th. So now we're moving on to chapter 2, and kind of the idea now is, well, chapter 1 was all about dealing with different kinds of data types and how to graph those data. In chapter 2, we're going specifically for quantitative data, and now trying to give more measures of the center, things like the sample mean or the median, and the spread of that data using things like standard deviation or interquartile range. And really chapter 1, chapter 2, both of them, the major takeaway is we're just practicing RStudio, getting comfortable with it, and some of the random terminology and things about statistics just to get us all on the same page. Well, any questions at all, folks, before we get started in chapter 2? How about folks over Zoom? Everything okay so far? Okay, we got some thumbs up. So looks like things are definitely working. Thanks, folks. And I definitely have not forgotten about folks in Zoom. One thing I should mention is I'm not great with Zoom, and this class isn't set up great for it either. Ideally, I'd have, say, 2 monitors so I can keep a closer eye on everyone that's in class, that kind of stuff. But we just kind of do the best we can. Probably the best way if you're coming into Zoom just to make sure you're getting the best experiences, definitely try to be active with the class as well. You don't have to have voice for participation. I'll try to pay attention to the chat as well. But the more you can try to be present and active throughout the class, the easier it will be, I'd say. Zoom always has that extra challenge. Well, I think we're just about ready to get started then, folks. Any questions or comments at all before we jump to chapter 2? Okay, looks like we're ready to go. So here's our chapter 2. I have here just the typical things. The Word document is for folks who don't have any issues with Word. I would assume you have Word installed on your machine. And then this document will work great. Same with all the lectures, all the assignments. This one's for compatibility.
Yeah, that's easy fix.
Oh,
Okay.
I had to change all the anti-quote.
Oh, brother.
Sounds like a different conversation. Let's mute those. So the PDF is really just for extra compatibility. So if you're seeing things print out weird, you probably want to use the PDF. And then any data set that we're going to use on the lecture is going to be contained down below. So that's our chapter 2. And here we are. It starts off with a wall of text. It's kind of gnarly to look at to begin with. But many of these things we're going to be really just computing using our big calculator, RStudio. So this is our opportunity to just actually name things, what we mean by a sample mean, sample standard deviation, and show about what the formula would look like. First, notation is a big part of this. So n, we'll always consider that to be the sample size. Anytime lowercase n comes up whatsoever, we'd have to say otherwise if it's not a sample size. If we indicate things as an x1, x2, xn, usually we're doing that only because we're describing a formula. So x1 will be the first observation in the sample, that's the second observation. If you have a sample size n, xn will be the last observation. Then if our data is nice enough, if it's at least roughly symmetric, we'll describe the center using the sample mean and the spread using the sample standard deviation. Well, to calculate the sample mean, we kind of mentioned what you would do just verbally. You would add all of the observations for your quantitative data, divide by your sample size. As a formula, this is what it looks like. Just do repeated additions, divide by n. Or the summation here is just saying repeatedly add up all those observations, xi. Either way we do it, it's a really fast operation in RStudio. So this describes our center. That's what we're meaning here when we say this represents a typical value in the data set. And if you want to describe the spread, you could use the variance. There's nothing wrong with the variance. And if you have taken probability, or you know you will, probability classes tend to work on the variance a lot more than a statistics class would. Only reason we're not as keen on using the variance is it doesn't have enough of the nice properties we would like. For example, if these data, your original pieces of data were measured in maybe miles for the unit, the variance would have a unit of miles squared, which is kind of a weird thing to try to resolve when you're saying how spread out your data is. But if you go to the standard deviation, this returns back to the original units, miles. So now we're describing the data with its same unit, making this much more preferable. So if we're calculating the variance, we would take these quantities, the observation, subtract its mean. So we're looking for the deviations around the center. Then we square all those so that the numerator comes out to something positive, non-zero. Divide by the sample size minus 1. And if you like formulas, that's what it would look like right there using summation. So that gives us our sample variance. And we get to the standard deviation just by taking the square root of s squared. And we call it s. Algebraically, that looks like exactly what it should be, since s squared can never be negative. Or excuse me, s could never be negative itself. So that's our rundown of these statistics so far. And I put here a couple remarks. Usually we know what we mean when we say the sample mean represents a typical value in the data set. It's the center in a certain sense. But I think the standard deviation is a lot trickier. The standard deviation is supposed to represent how spread out your data is. But when you get that number, here's how you can think about it. About 95% of the observations in your distribution that's symmetric, mound shaped, should be within 2 standard deviations of your mean. So that gives us an idea of how spread out the data is as soon as we calculate the standard deviation. Well, that's a lot of formulas, but this is what we're going to be doing essentially, not using the formulas directly, but we have to know what they represent. And so this example 1 is just a really fast problem getting our hands dirty calculating these statistics. So it says, consider the random data given below. It's definitely random. I don't even have context, but I threw it in units just to mention that nice fact about units with the mean and the standard deviation. What we want to calculate is sample mean, sample standard deviation, and we need to use the correct symbol when we report those values. So now let's get RStudio going. Let me rearrange these windows a bit. Okay, so there we go. So there's our data right here. And for RStudio, we don't need to use the import button that we typically did if it was a larger data set, like we did on some of the problems and the assignment. If it's something like this, just several observations, probably the fastest thing to do is write out any variable name. You could call it just generically X if you like. I'll go with sample. Left arrow is going to now store in sample all these data here, but start with C to combine them. Now we're making a vector of data. And we'll type in 5, but we must ignore the unit, just 5 itself. 13, negative 12, 7, and 2. So now our data is there. And to get the sample mean, all you really need to do is write mean of the sample. You could store this if you know you're going to use it on a further operation, but if you just need the mean, usually I would write out this way. This is just going to output the result down here in the console for us, rather than storing a new variable. Now for the next one, it wants the sample standard deviation. So if you want a standard deviation, go SD, and that's the right function, SD for standard deviation. Type in sample, close the parentheses, and this will do everything for us in one shot. So let's hit Control A, Control Enter to run all of this. And here's our output down below in the console. It says the mean of the sample is 3, and the standard deviation of the sample is 9.3. Oh, we've got a question, and Olivia says, I assume we should also practice calculations on our calculator, as we can't use RStudio on the test. Well, when it comes to an exams, if I need you to do a sample mean, I would provide that actual value on a real exam. So this is not something you would have to practice doing by hand in this class. Does that make sense with that question there, Olivia? You betcha. Thanks for asking about that. And yeah, that's one thing that's kind of strange about this class. We're using pretty powerful technology, RStudio as a calculator, but anything like this where I have to do a big number crunch or produce graphics, all those things are going to be provided on the exam itself. Essentially, your exam is really going to be concept questions primarily. Other questions at the moment so far, folks? Okay, well, there's lots of ways to write down your answer. So this is going to look a little bit weird. We're going to write down several different options. Let's call this one option 1. You might just write it down. This could be done digitally. This could be done with paper and pencil. And if you did it that way, let's write down, once I get my colors going, sorry, one moment. There we go. We'll write down X with a bar. So there's our X bar. That's the mean of the sample. And it came out at 3. So 3 inches. Next, our standard deviation down here is this quantity. So we'll write S for the proper symbol equals 9.3 inches. And here, I'm not really picky on inches, but oftentimes with statistics, if you can throw in the unit, it can help a lot. It's surprising because we have to interpret a lot of our computations. And this brings us back into the context of the problem, just mentioning the unit. The major reason I put the units here is just to observe if you're using the standard deviation, we'll have the same unit as the original data. So that's option 1, just write it down. The second option could go like this. And this is definitely optional. So if you're not very keen on using Microsoft Word, especially the equation editor, don't worry, there's no need for doing that. So you could either write out X bar equals 3 inches, S equals 9.3 inches, and that would always be completely appropriate. If you write out X bar like this, sure, it doesn't look super wonderful on paper, but everyone's going to know exactly what you mean in this class. And technology shouldn't be a limitation. You can just write it down, type it normally, like if you're writing an email, and I'd be okay with that. Still an option 2, if you like the equation editor, you can always ask me about it. The way to call it up on Microsoft Word is you have to hit the Windows key and the plus key simultaneously. I think, let me try, oh, that was the wrong key. Let me hit escape on that. Whoa. I hit something on my accessibility, I think. Now, how do you exit this? Oh no. I'm not completely certain how to exit this super zoom in for accessibility. Oh, there it is. That's the magnifier. Sorry, folks, 1 minute while I try to exit out of that. I don't want to pin it. Close. Okay, we're out of there. Now, what were we doing? We were trying the equation editor. So again, it's not something you have to do, and it could cause problems with the computer, apparently. But you typically hit the Windows and the plus key. Typically. What in the world? I've had some weird issues with this. Let me try one. Oh, it's not Windows plus. There's my mistake. Alt and plus. That's strange. You do that like a million times a day. It's become muscle memory. Like you must have forgotten how I actually do it without really doing it. So if you hit the Alt and plus key, you get this equation editor right here. And it's more intuitive than it looks. There's lots of shortcuts that just make sense. You could write out X, then a slash that direction with bar, a space creates the bar, another space centers it on X, and you can say X bar is 9.3 inches. Then S, well, we wouldn't have to do anything special there, is 9.3 inches. And you can just type up your answers like this using the equation editor. If you're curious about that kind of stuff, email me anytime and I can send you documents on doing more of this kind of thing. But again, it's just an option. It's not required. If you see me typing down things like this, don't feel as though you have to. Any questions at the moment, folks, with different ways to pull in those values? Okay, the third option would go like this. I think the third option is the only one that definitely just needs a little bit of extra clarification. only screen capture what is relevant. Relevant to the question, in other words. And so what we mean by that is, let me put this window over here somewhere. You could just take a screen capture right here, and I would be okay with that. Even highlighting and copying, that doesn't work too bad either. Sometimes formatting does break down if it's outputting a lot of results. So copy pasting tends to be the least favorable value or way to do it. But if you hit the Windows, Shift, and S key simultaneously, just go around here. Only give the portion that is actually relevant to the question, the mean and the standard deviation. And you can just paste it right into your document. And that would be okay as well. I mean, it's saying which is which. It didn't have the correct symbol, but that's okay. It was more labeling each thing correctly. So we did it, folks. We calculated the sample mean, the sample standard deviation. That would have taken, for these data up here, probably a good 15 minutes if we were doing it by hand and being very careful. Any questions whatsoever on getting those two values out so far? Okay, well, this one was, again, just for fun, getting used to the technology, seeing it in RStudio. Let's try it next on a problem that would be more of a typical homework problem, actually. Our homework problems are almost always going to have context, so they usually look something like this. So this problem says, a veterinary anatomist investigated the spatial arrangement of the nerve cells in the intestine of a pony. That sounds grim, but could be important work. He removed a block of tissue from the intestinal wall, cut the block into many equal sections, and counted the number of nerve cells in each of the 23 randomly selected sections. So this is a lot of work. Probably graduate students helped him do this massive endeavor. But here are the counts. It says number of nerve cells. We really have just one variable. It's quantitative. And each one of these is an individual in the data, but it's corresponding to essentially a slide of intestines between glass that they counted the number of the nerve cells on. So for that particular slide, 34 cells, some of them on the lower end, like 19 cells, 12 cells, and so on. So we've got all of our data there. And if you're interested in this kind of problem, this is definitely not good enough. We want to know the shape of the data, and then we want to characterize it by describing its center and its spread. Well, let's give that a go. First thing we'll do is display the data and describe its shape. So back to RStudio on this one. Let's see if I can make these a little bit closer. First thing we need to do is import the data. Oh, and before I forget, I want to try to get in the habit of always outputting this stuff that we did in RStudio. So if I ever forget, don't hesitate to remind me. And if I did forget completely, I might edit the notes just to make sure it gets brought in some way, somehow. Okay, so there's our syntax from the prior problem. Now let's get back to the ponies. And first thing we'll do is import the data. Probably not a bad idea to clear the whole environment. You can use this broom icon to make that happen. Now, the import, click here. First option is the right one. And wherever you have your data, let's point to, for me, it's on the thumb drive. We're in chapter 2, and we're on example 2. I'll try to pretty much do all my data sets in this kind of way. Exercise 1, problem, example 2, and so on. So like before, you really don't have to change any of these options. You might change the name, but that's not even necessary there if you don't want to. Let's hit import right on this window, and now we've got all of our data. I usually close off that tab. I typically expand this, but this is kind of a weird data frame. It contains exactly one column of data. It's kind of burdensome to call up this one column of data. And so here's a strategy you could use if you like. All we care about is the number of nerve cells per section. So let's call the new variable cells. And I'm just going to try to extract this number of nerve cells out of the data frame. So sales will get left arrow. Safest way to do this is start typing out example 2 slowly. You'll call up the full thing, hit enter on that. Now, notice that $sign right there. That's the hint in RStudio. That's the next symbol you want to type in. So shift 7 for the $sign. Or no, that's shift. Where did my $sign go? Shift 4. The moment you hit shift 4, this new window comes out. And if you hit enter on this, you're typing in that entire description verbatim, which is good because it must be typed in verbatim, or else we won't be pulling in the right data or anything at all, really. So there it is. It's not a bad idea to run this right away just to make sure it was successful. So with Control A, Control Enter, we have cells, 23 observations, and their integer values. So that all looks correct based upon our data right here. See if I can scroll there. There we go. Well, now that we have that, histogram is a pretty fast operation. We'll just write hist to pull the histogram. First option is going to be where your data is. So this time we'll just call cells, and that'll do the job. We run it just like this. We're just seeing how the graph turns out. Frequency is correct. For our histogram, it's just saying how many of those sections of the pony's intestine landed in these different ranges. So if you're at the red dot, between 20 and 25 cells, that was 4 sections had that count. If this said cells here, I'd probably be okay with that, but I think it would be better form to take this entire title and type it in for the real title here. So let's write in xlab for xlabel equals, and in quotes, number of nerve cells. Okay, so there's our input there. Let me move this just a touch. But the trouble with this is if your title gets a little bit too long, the graphics could break here, but there's always going to be a way to fix that. Let me see if I can kind of demonstrate it. So I'll run it just like this. No, it actually fit just fine. But if your title didn't fit, one thing you can do is use the export key here, go to copy to clipboard, and this is a better environment to try to resize everything using that little hatch right there. Just left click and drag it around until it looks about right. What you wouldn't want to do is give a graph that, well, RStudio doesn't want to do that either. You don't want to necessarily compress it too much because you do want to see the changes in the height. And you don't necessarily want to go too much in that direction either, or else part of your graphics, like your title, could break. You're losing information on the scale. It's kind of hard to tell where 30 is even centered at in this point. So try to go for a decent balance, and I'd say that would do the job for us. One thing I noticed is I did try to update this machine, but I cannot update RStudio without administrator privileges on this workstation, so I'm going to have to work with IT on it. What I typically do is click copy plot right here, and I'll go back to the Word document and paste it in. This works at home, but it's not working on this workstation, either RStudio or Microsoft Word. It might be out of update. But if you paste it in right here, merge fat formatting didn't work, you should see your graphic. Definitely didn't work. So let me go back to RStudio. Instead of doing it that way, I'll just take this as the graphics we'll use, hit Windows, Shift, and S simultaneously for your screen snipping tool. And I usually take away the main title. That's not something I'm picky on, but I feel like we know it's a histogram. We know what the data is. That's not even a great title. So I usually just let the graphics be this much right here is evident what we're dealing with. You don't have to, well, you don't have to resize it, but if you want, you can zoom this down a little bit just to save on some real estate. And next what we'll do is describe its shape and then go and calculate some summary statistics. But any questions, folks, on producing that histogram down here? Okay, I've gotten lots of homework back and looks like people are not having too much trouble with that at all. Maybe just one reminder, just as a blurb. RStudio is just a tool for us in this class. My goal is to not put so much credit on RStudio that it feels like this is a real burden to getting through the course. So if there's anything that you ever get stuck on, maybe it's producing this graphic right here, always feel free to reach out and I'll be very happy to give maximum support on that. I'll tell you exactly what the syntax is or what might be wrong. And if we can't figure it out, I'll just give you the graphic to use in your assignment and we'll try on the next one, especially if the due date is coming up. So don't feel like you're losing out if you're struggling with RStudio. I'll always try to help out. But let's get on to the shape of this thing. The major thing I'm worried about when I'm asking about shape is it symmetric or is it skewed? Any volunteers for the description on this one? One question you can ask yourself though is, if you worried it was skewed, would you say it's skewed to the left or to the right? Or do you feel like it's kind of a toss-up? If you feel like it's kind of a toss-up, there's not a dominant direction where it's skewing, you're dealing with, oh wait, let's not spill the beans, we've got a chat. I agree with Olivia, you're dealing with symmetric data. There is a slight left skew, but this left skew is not enough for us to say these data are symmetric. In fact, we would call these data, imagine this is your capstone project as, say, an undergraduate or a graduate student. If this is your data and it looked like this, that's practically a celebration. We would consider this to be highly symmetric data. I forgot to start off with a bona fide sentence. Let me go up here and say, these data are highly symmetric. We do have, as Olivia mentioned, a bit of a blip right here, which could be considered a slight skew to the left, if any. But for this picture, it wouldn't really be even worth mentioning. I would just say highly symmetric is the major thing that's relevant here. Now that we know it's symmetric, here's the reason why we're making such a big deal out of the shape of these histograms. Because the data is symmetric, we will use X bar and S. So those would be the summary statistics we would use to describe these data. And if there was more skew, we might have still potentially called it roughly symmetric at a certain point, and we would still use these two statistics, the sample mean and the sample standard deviation. It's only when skew becomes a major problem, and we will see it in these notes. I have some nasty looking data. Once skew becomes absolutely apparent, we have to change these statistics. The sample mean will not describe the center of skew data, and standard deviation does an even worse job of describing the spread. Specifically, what goes wrong with S is this description right here, that approximately 95% of your observations in mound-shaped and at least roughly symmetric data would be within 2 standard deviations of its mean. That falls completely on its face. If your data is skewed, that statement is just outright false. Well, now we can go to the last part of the problem. It says, describe its center and its spread numerically. But what we'll have to do on this assignment is we need to look at the data and decide which statistic to describe the center with. That's what we're studying here. We're going to use the sample mean, and we'll see more statistics on these notes that we'll use for skew data. So the problem will end the moment we write out whatever the mean of nerve cells in the intestines, Poni's intestines are, so that's X bar, and whatever the standard deviation is for those nerve cells. But it's just a couple really fast operations and back in RStudio, so let's go over there and crank them out. First, any questions or comments, folks, about our descriptions here? Okay, so back to RStudio. I think we can kind of minimize this now since we're just focusing on statistics. So I'll minimize my graphics. Next thing we need is, because I stored it all in cells, I'll write mean and then cells. Then SD for standard deviation, input cells once again, and that's will output everything we need to finish the problem. So let's hit Control A, Control Enter, and I'll hide that again. There we go. So there's our mean, there's our standard deviation. And in this course, I'm not very picky on how you round these things. I'd say use your best judgment and round appropriately. And if there ever is a problem where rounding becomes more of an issue, I would write it into the problem, round to so-and-so decimal place. But I think that's usually, if you're using your best judgment, that works pretty well for this class. So our sample mean is this value here, 26.57 cells. And before the deviation, we have a chat. Sydney asks, if the data is skewed to the left or the right, would we still use X bar and S? For something clearly skewed, either left or right, instead of X bar, we're going to be using the median, which is the 50th percentile of the data. And instead of the standard deviation S, we're going to use something called the interquartile range. So that's the next wall of text down in the notes below. Does that make sense with that question there? Awesome. Other questions at the moment so far, folks? Okay, thanks for those questions at the moment. Those are really kind of the major part of the homework assignment of knowing which statistics matches with which shape of data. So let's report our standard deviation next. I'll round this one again to 2 decimal places, 7.05 cells. Well, we did it, folks. That's our description of this problem. And really the whole thing we're trying to do on these notes is, or this whole chapter really, practice RStudio and work on different statistics to match with certain kinds of data like these. Well, I think we've got it, folks. This is the end of the problem. Let's get that syntax in here. Still getting used to working on this particular computer. Okay, well, that's one problem down. And this one is more of a typical problem that you're actually going to see for the homework assignment that's coming up. For the next problem, we're going to get a little bit more in line with that issue that we're talking about of problems with data. Now, one thing that's kind of challenging in this class is we routinely say things along the lines of at least roughly symmetric. If your data is at least roughly symmetric, we like X bar and we like S. But once data becomes clearly skewed, and this is what we mean by clearly skewed, we have to change our statistics. These are some nastier looking data, but it's real world data, so let's take a look at what's happening here. It says the 2015 Urban Mobility Scorecard from Texas A&M included data on the estimated cost in millions of dollars resulting from traffic congestion for different urban areas in 2017. So for example, if we look at this row for Houston, there was a $5 million loss they're estimating as a direct consequence of traffic congestion. And that was in year 2017 specifically. It goes on to say next, the following data are for the 13 largest urban areas that have population over 3 million. So this is not a random sample at all. If all we cared about is the 13 largest urban areas, well, this could be our population in this problem. So it's kind of an exceptional problem for statistics where we are not dealing with a sample. There was no randomization on this one. But still, if we were doing the study and we had to work with this data, first thing you'd want to do is produce graphics like we did with the ponies. And here it is. So total cost lost due to a direct consequence of traffic congestion. Here, we don't see the actual urban area. This is the identifier variable. We're just seeing the quantitative variable here represented. So between $2 and $4 million, that was 8 cities. But some cities are more exceptional. Some cities are losing between $14 and $16 million. That's got to be New York, or Los Angeles is in this range as well. But either way, I would definitely say these data are clearly skewed. But question for the class, is this skewed to the left or is it skewed to the right? I agree. This is looking like right skew data. And over the chat, yes, absolutely. Thanks for responding, folks. So the way we can tell is skew is all about the tail of the data. or where it's trailing off. It's trailing off to the right, and so this alone is what's giving us the right skew. So let's put in here. These data are right skewed. And for these particular data, I would probably add a little bit extra here. Any volunteers for what you might want to say extra after just saying skewed? One way to think about that question is, when we talk about the shape of the data, it's not just these pictures you see here. Another important skill is, let's go up to a prior histogram. When you see this, if you feel like it really was highly symmetric, imagine drawing a curve superimposed on the data itself. It might go about like this. So there's our highly symmetric data. It seems to fit with a symmetric curve in a nice, decent way. Olivia says the significant increase in the frequency in the 2 to 4 million range. It wouldn't be as much about that, but that's definitely the interesting part of this data. This is what's causing the skew. We try to put a curve to these data, it might go about like this. It has to jump down very, very fast. Well, let me try again on this. Has to jump down to match the skew. And then that shape might be about like this. One last try. Just trying to give it a good, honest shape. If I was going to put a curve to these data, it would look about like this. Now, anything around here, I wouldn't say is exceptional at all. But once you're getting far from the main packet of data, these ones are exceptional. They're so unusually high compared to everyone else, we're going to call them outliers, or suspected outliers might be the better thing to say here. Let's put here for our next description. There are two potential outliers. So data that's leaving the main grouping is always something we ought to mention. And I use the word potential outlier here because, well, the moment we see something exceptional, a lot of extra work has to be done. There could be a reasonable explanation for this. Maybe for some reason, a digit was put in the wrong place and New York is not as bad as it seems. Or maybe the wrong cities were being aggregated together into one. There could be a lot of explanations for this. And, well, we also have rules of thumb to help us out. There's going to be the 1.5 IQR rule of thumb for determining if this really is an outlier. So always watch out for these kinds of things in your histogram. If we turn up for just a moment to the prior one, I'm going to erase these for a moment, but just to give more advice on histograms and outliers, if there was a rectangle right here, I wouldn't call this one an outlier. It's not separated by much from the main pack of the data. So just because there's a gap in your data doesn't automatically tell you, oh, there must be outliers to the left or to the right of it. What you're looking for is something more like this. I would say about here is where it's starting to look a little bit shady, and the further it goes to the right, the more it's going to look like an outlier. So you're wanting some extra honest separation from your values you're thinking about and the main pack of the data. So in our current situation, for what we have here, I would definitely say these are skewed to the right. There's nothing symmetric about it. And these were so far out that we should mention them. Those are the potential outliers in this problem as well. If this was, say, an exam problem and you could have lost points for not saying potential outliers, I would have written into the instructions, mention outliers if you see them as well, just to make sure we're on our guard for that at the same time. Well, any questions, folks, with our part A here? Okay, now here's what goes a little bit sideways for these kinds of data. It's quite skewed to the right. Oh, I do want to leave this yellow. And so if we want to describe where the center is, we can still do it. It's not so bad. If we were to describe the center on these data, well, it'd be where about half the area goes to the left of this dot and half the area go to the right. So at this location, maybe somewhere around here, if I was visually estimating it, I would say that spot ought to describe the center. We put in a line segment that goes up. It's cutting the area to the left and to the right just about in half. Well, at least visually, that's the best place I would indicate it ought to be. But that's why we have our studio. We want to calculate that location definitely. And just to see what goes wrong again with these data, let's actually calculate it. Let's calculate the sample mean of these values here and see how close we are just visually. So back to our studio for just a moment. I'm just going to delete this, and it'll be a fast operation. I'll write this generically as x gets. This is the tricky step, carefully typing these in. But don't forget to begin with C. Combine all these data into a vector, put in an open parenthesis, and then 15. 13, 7, 5, 5, and let's take a look. 1, 2, 3, 4, 5 4s. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I think we've got them. Let me go to a new line. 3 3s. And we want the mean of x. So the mean of x and for these data is 5.6923. Let's take a look. We estimated, well, I did. I hope you all agreed with that. The mean or the center should be about here if we're doing it visually, like on assignment 1. But if you go to calculate the statistic, the sample mean, 5.69, is actually pretty far to the right. It's somewhere around here, I'd say. So the sample mean got fudged. And this is not a coincidence. The sample mean will move in the same direction as the skew. We were skewed right, so the mean moved from where we would thought of it as the center towards the right in this location. The sample mean is no longer doing a good job representing the center. So let's write this down here. Explain why the sample mean should not be used to describe the center. We can say the sample mean is pulled far to the right due to the right skew. So what we really need is a whole different statistic. And it turns out this statistic here, that's just the median, the 50th percentile of the data is what will always do a great job to describe the center, even if your data is highly skewed. That becomes the better statistic. So that's what's going wrong here. And then when it says, explain why the standard deviation S should not be used to describe the spread of these data, there's a couple things you can answer with here, but one quick way to answer it is you could simply say the formula for S involves the sample mean X bar, and so it is no longer reliable. The whole idea with the standard deviation was we were measuring the deviations of all of our data from a central value, the sample mean. But if the sample mean is no longer describing that central value, all of this falls down on its face, and S is no longer doing a great job measuring the spread of these data. In fact, it would give us some really weird results. So that's our problems with these data, and the only way to fix it is we need different statistics altogether. Well, any questions at all, folks, with these problems here? Okay, well, just a preview for the notes, and in case you decide to start assignment too early, this is essentially what we're going for at the very end of this document. We're going to fill out this table here, and the way it's pretty much going to go is, if you're at least roughly symmetric, for the center, we'll put in X bar, and for the spread, we'll put in S. There's this uppercase M here, that's the median, the 50th percentile we've been mentioning. And if your data is at least roughly symmetric, you will find that X bar is going to be approximately equal to M. Not a much difference between the two statistics for at least roughly symmetric data. And that's the reason why we'll always use X bar and S. Those statistics are easier to work with calculus has been used to give us statistical methods based off those statistics, and the power of your tests are higher if you're using these two statistics here. These are sometimes called parametric methods. But if your data is skewed, you change the statistics to these things, and we start using something called non-parametric methods. They still work, but they lose a lot of power. Your conclusions wouldn't be as strong when you go to those different methods. For those reasons, we're highly forgiving when it comes to symmetry. That's why you see at least roughly symmetric so often. And it's when data starts to look like this or worse, that's when we have to change our statistics. There's no other way to really handle this data without transforming it. Well, that's our rundown for this problem. What we're going to be going down to next is our brand new statistics for skewed data. The median and the interquartile range are going to be our two statistics. So let's see how it goes. First, with median, it says the median is attained by, first you would order the n observations. This is only if you're doing it by hand. Then the actual by hand formula would go like this. If you have an odd amount of data, your median m is just the value in the middle. If your data is even, you have two values, you would just average your two central values, and you're getting the median m. But if we're being honest about this, the median m does not have a unique formula. Its sole job is to approximate 50 percentile, meaning it's one number that cuts half the data to the left, half the data to the right of it. But there is many different numbers that will do that job. If you calculate this by hand, well, that method could differ on the formula that would be used in RStudio. RStudio has some slightly different methods on calculating the median. So there's lots of different formulas for this, which means we will only ever do this by hand. I will never give you a problem that tells you, excuse me, I said that wrong. We will only ever calculate the median through RStudio. I'll never ask you to do it by hand. Let me say that again. I won't ask you to calculate the sample median by hand, certainly not in an exam. That'd be rude. Interquartile range, you might have to, but it's just a really fast formula, taking the difference of these two things. Okay, so median is the 50th percentile of the data set, like we've mentioned. It's just cutting it in half. But then we go to this thing, Q1 for the lower quartile, Q3 for the upper quartile. Only difference between those things and the median M is that Q1, the lower quartile, that was just the 25th percentile, and quartile 3, that's just the 75th percentile. The wording here is really weird for some of these notes, so I just have to be really upfront about that. A very common question is, what happened to quartile 2? That's M. M we just think of as quartile 2. That's why it goes 1 and 3 in that kind of way. So this is all about the position of the data. M is the number that cuts it in half. This is the one that cuts it in quarters, giving you the lower quarter of the data. Q3 will give you the upper quartile. And finally, that takes us to the interquartile range. This is a distance that captures the central 50% of all of the observations in your data set, approximately. These aren't necessarily dead on 50%, but just as close as it could be made based off the number of observations you have. So the interquartile range is going to represent the spread of the data, and the median is going to represent the center. But like we mentioned before, we would really only ever use these things if we know our data is skewed enough to warrant it. Well, any questions, folks, with those formulas at the moment? Okay, well, first thing we have to do is just practice it with this random data set right here. What we're going to produce is a so-called 5-number summary. It's not going to give us just these 3 values. For the 5-number summary, we'll also have the minimum and the maximum. Then, after we get that summary, we'll use a box plot to display those numbers right here. So let's start with the 5-number summary. Let me rearrange again. kind of a bother trying to get these windows to work sometimes, but think of this as a really fast mental break while I'm fighting with the windows before we go to the next problem. A little bit of a mental break in the middle is not a bad thing for these kind of classes. Okay, so let me wipe these out. We can clear off this. The first thing we want to do is import all of these data. Move that over here. So here's the 5 observations. We'll go, I'll call this sample again. So the sample gets combine 113, 124, 126, 128, 131, 133, 135. So there's our sample. Next thing we'll do is, it's asking us right away, what is the 5-number summary for these data? So we want minimum quartile 1, medium quartile 3, and maximum. But you have to remember with RStudio, this looks like we're going for 5 functions altogether, and that could work. RStudio is written for statistics primarily, so there's always a fast way to do this. Summary sample is what's going to do the job for us. So if you use summary here, hit Control A, Control Enter, it gives you right away that 5-number summary. Now, if you took a screenshot of this as it stands, I would be okay with that if you responded like this. Because in this format, I can tell that the minimum is 113, first quartile is 125, and so on. It's apparent what is what. What you should absolutely avoid, though, is if you go like this, highlight, copy with Control C, paste with Control V. Well, you know, it didn't look too bad here, but sometimes it breaks. If you notice the formatting doesn't even look right, you might have to fix these a little bit. But typically what I would do for this kind of problem is really just write it out. I would go minimum equals the 113. Next is quartile 1 equals 125. The center, the medium M, is 128. Quartile 3 is 132. I thought I'd fit them all, but here's the maximum at 135. So there's our 5-number summary, and essentially tells us exactly where all the data lies, but it gives us even more because these are percentiles, the 25th, the 50th, and the 75th percentile. Well, now that we have that, next thing we want is a box plot. But RStudio probably, if you start typing out box, you're probably going to get exactly what you want. Here it is, option 2, box plot. Include sample, and we should be all set. We just have to do the typical things of fixing the axes where needed for these kinds of graphics. If you've never seen a box plot before, here's our newest graphics. Let's hit Control A, Control Enter, and here's our box plot. Now it's definitely has a couple issues with it that we need to correct. There doesn't have to be an axis going this way, which is already a little bit weird. What you would have considered as a horizontal axis has converted into a vertical one. So we need a label going this way. Let's see. Well, we would have, but you know what? There's no context for these data. Let's leave it like this as it is. And with a problem that does have a context with a meaningful label, we'll be sure to include that one. So here's our graphics. With a quick screenshot, here's our data displayed as a box plot. Well, any questions, folks, with producing this graphic here? Okay, let's go back to, well, let me make sure we're just about done with this problem, that we get the syntax in. Now that we have a box plot, we should definitely pause right here and stare at it for a bit to know what in the world we're really looking at. The box plot is just a way to graphically represent this 5-number summary. So you'll notice that our minimum value is this one right here. This value here is going to be the minimum after removing a suspected outlier. That's one thing that's already surprising about these data. To me, when I look at this, nothing even looks exceptional here, but 113, it was exceptional. It's far from the original pack of the data. And so RStudio itself is calling this thing an outlier. Next thing we have is this heavy line right here. That's your median value. This is what's cutting the data in half. Next, for the lower edge of this box, that's quartile 1. Upper edge is quartile 3. There are no outliers in the upper end. That's why there's no circles like the one down here. And so this is the actual max or maximum of the data. So that's what we're staring at each time we look at a box plot. Well, now that we have that, the minimum here is calculated in a very specific way. What we've done is use the interquartile range. Then we multiply the interquartile range by 1.5. Any observation that's more than 1.5 times further than the upper quartile is a suspected outlier. Any observation that's below 1.5 times this quartile, or excuse me, below quartile 1 minus 1.5 times the interquartile range, that would be a suspected outlier, and that's what we're seeing right here. So RStudio in this one graphic calculated the 5-number summary, displayed it in a box plot, and it even used this rule of thumb. It found a suspected outlier right here by this formula. And you're welcome to do it the same way in class. If it's asking you to calculate or find a suspected outlier, you're just looking for anything that falls more than 1.5 times the interquartile range below first quartile, that was this one, or above the third quartile. RStudio will flag them immediately. So again, this is something that you can just take advantage of RStudio with to calculate and find these values. Let's say here, just to be specific, this is a suspected outlier. By the 1.5 IQR rule of thumb. It's a fairly accepted rule of thumb, but it's definitely only a rule of thumb. It tells us this is the place to start looking if there's problems in your data. It's flagged something that is unusual. Well, last thing we ought to talk about is it uses 1.5 times the IQR. Let's take a look at the IQR just one more time. It's not represented on this graph specifically, but it really is in a kind of way. Interquartile range is quartile 3 minus quartile 1. Here's quartile 3, here's quartile 1. And so the distance from here to here is IQR. I'll identify it this way, just a line segment going up and down. So from here to here in distance, that's the range of how far the central 50% of your individuals in the data set take up. They go from here to here. The bigger that range is, the more spread out your data, and the smaller, the less spread out. And for the rule of thumb, it was decided that take this 1.5 times as much, that's a pretty good ruler. Anything below Q1, 1.5 times this quantity, like this one is an outlier, and anything 1.5 times this length above quartile 3 would have also been considered an outlier, but there was none in these data. So that's our rundown of the brand new statistics, a 5-number summary, and a box plot all in one. But the box plot is fantastic. It calculates a whole lot of stuff for us. Any questions at all, folks, on getting through this problem? Okay, this is one of those problems that had no context with it. So that means it's probably not a good homework problem. Usually homework problems look more like, say, this one on example 5. Let's take the rule of thumb with this, why not? This is an interesting set of data, and you had one in your homework problem as well, where you are looking at a variable like this one, but the identifier variable is year. It's really time series data. Our course isn't going into time series, so we really just focus on this variable here, just like with the homework. But here's what it's saying is going on. Recruitment is the addition of new members to a fish population. It's an important measure of the health of ecosystems. That's just pure context, so let's put it a page break here. And that was extra space, never noticed that. It says next, data on the recruitment of rock sole in the Bering Sea. So that's a nice fish. From 1973 to the year 2000 is given in this table below. This table is weird because the more you look at, you might notice, I think a year is missing. 1992 is not on there. So I'm not sure what happened in 1992, but maybe something broke down in the reporting. First thing we'll do is get a feel for these data by looking at a box plot. Here, we're not looking at the shape as well as we might be on a histogram, but we can still determine symmetry versus skew. Well, let's start off by placing all these data into a histogram and go from there. Any questions first, folks, with the data or otherwise? Okay, so back to RStudio, we need to get this example 5 imported. First, I'll just wipe out all this, delete that out, and for importing, let's go slow. We haven't done this a ton. Click on this little Excel sheet thing. First option, then go and hunt for your data. We're on example 5. So wherever you download this file, just double click on it and just click on imports right on the screen. So now we have year data. This would be useful for doing time series, but we're really just going to focus on this variable right here. So we're interested in the recruitment, and let's go with this strategy once again. I'll just call this REC for recruitment. Left arrow to say recruitment gets. Start typing out example 5. Hit enter here, then the $, and go to that second option with the up-down cursor keys. Hit enter on this one, and we've got it, folks. That's the variable extracted. Hit Control A, Control Enter, just to double check it came out right. Yeah, we've got 26 observations for recruitment. They're all integer values. So now we can go, well, it asked for a box plot. So let's go box plot, REC, to see what that turns into. Now that we've done that, here's our graphics here. And now these data do have context, so we should say what all these numbers right here represent. Those numbers on the horizontal axis going this way came from here, recruitments in millions. So we need a label that describes that. I'll just type out verbatim recruitment in millions. So back inside the function, put in xlab for your x label. You know, that's a mistake, right? I'm just used to thinking of x label for quantitative data, but no, this is the y label, the vertical axis. We should go y label. So the right orientation, y label gets recruitment in millions. So that should give us a decent box plot to work with. Let's run this again and see what we've got. Yeah, that should do the job. Click on export, copy to clipboard if you want to resize it. For box plots, I'm not too worried how you resize these kinds of things, but typically when you're dealing with a box plot, there's usually many side-by-side different box plots going along with it. This one does seem kind of odd just being the way it is, one plot right here. Well, let's take a quick screen grab. And back to our document, here is our results. Here are our results. Well, any questions, folks, on producing this box plot here? Okay, just like on the other data set, there is an exceptional value. This one would be the suspected outlier. But now it says on part B, comment what you see in this display using the context. Let's highlight that. It's easy to miss the context when it's being asked for. And this is a problem written more in a style, say, like a real exam question, less a homework question. If this was an exam question, I try to give you good advice on how much of a response you need to give. Sometimes I might say, briefly explain. That's just a hint to say a one-word explanation might even do the job. But here we're looking for 3 different things that we would want to mention here. As long as they're correct on the graph here, you are going to have a full credit on your response. So different people in this class might mention different things. I'll turn it over to everyone in the class, whether you're in Zoom or in person. Anyone see something that you want to mention right away for these data, if you're just looking at that plot? Good call. I would say this is always something we should mention. Anything that just seems atypical about our data is always noteworthy. It's an outlier in the super high end. So looking at the data again, anything that was really high, above 4,000, well, we have one right here. That's one observation in 1987. And Olivia mentioned, yes, definitely we want that outlier. So looks like that's our outlier in the year 1987. We look at the data in 86, it was 2809. Then it jumped up massively, and then it jumped back down even more in 1988. There was actually a geological event right here for the rock sol. That's what's causing this. If we actually put these data into a proper time series, this looks less remarkable. So sometimes outliers purely depend on how you graph the data. But in a box plot or a histogram, this one's going to stand out by a lot. So let's go here just to start. There is an outlier in 1987 with 4700 million fish recruited. Kind of a weird word, but I'm not going to argue with a biologist with it. I'll just keep on calling it recruited. Million fish recruited. We've got one thing down, and well, we still want to say more about these. We're going for 3 items. There's our first item. One thing you could mention is symmetry versus skew is not a bad thought. We're not looking at a histogram, but it could still be done with a reasonable amount of accuracy. Any volunteers for what you would say here? Would you call this roughly symmetric or skewed in a particular direction? It's definitely skewed, but this one turns out it's going to be skewed to the right. That's right, Olivia. So yeah, absolutely, we have skew. This is a tough one to resolve skew on. It's spread out more in this direction, and that's the upper end on this axis. So if you think in terms of rotating your head to look at it just right, it's skewed towards the positive or towards the right. So we can say here, the data is skewed to the right. And again, this word context is tricky. All I mentioned is skew to the right. There's no context in there. But we mentioned at some point, we're talking about recruitment, particular years, 1987. As long as you're mentioning what's going on in the study, talking about the original context, I would still give full credit to this right here. Let's leave it in as is. When I say use context of the data, you just have to mention the original context somewhere as you go through. Well, we have skew, and we still want to say one more thing, but there's really a lot of things you could say here. For example, this is the median value right here. So you could say that the 50th percentile is that number of fish, whatever that looks like it would approximate to. Or you might say instead, 50% of all the observations go from here to here. You're using the interquartile range if you went that route. That's a decent thing to mention. Or you could talk about the minimum value, the maximum value, maybe not so much. That one, we already mentioned it. Let's go with the interquartile range here. We can say that about 50% of all years in this data set saw recruitment between Now here we might make a bit of a judgment call. If you're doing this like you might do on a real exam, this could be a real exam question where the plot is already provided. You just eyeball this and give me an approximate value right here. If you want, you can go to RStudio and just do summary and get the actual value. Let's do that just to demonstrate. You might go summary, REC for recruitment, and you could use these exact values down here. But if you're looking at a plot and it just says comment what you see on that display or that plot. Sorry, I lost my pen and tape. What in the world? There it is. If the instructions just say to do this, comment what you see on your plot, it's okay to just visually estimate what you're seeing right there. I'd be okay with that since that's about how the exam question would go for this type of problem. So let's say between about down below here, if we're visually estimating it, I would think of that as about 500 million to, on the upper end, let's see here, maybe 1,500, maybe a little bit more. But if we're visually estimating, as long as you're in the right ballpark, you'll get full credit on that kind of response. So I'll go with 1,500 million. Well, that's our description of the data. It's missing something critical, the actual time component right here. But again, our course is skipping the time series analysis. It's a very tricky subject just on its own. Well, next it asks us to follow up on this question. What statistic best represents the center of these data? And which statistic best represents the spread? This is a question I do ask on exams, and this has been one of the more confusing questions. Because when you see this, what statistic, a lot of times people want to calculate a value. But here we're just saying which one is going to do the job to represent the center. We have two competing values for center. It's either the sample mean X bar or the median M. Any volunteers for which one we should use? Exactly, because we said the data is skewed to the right, in fact. We'll use M to measure the center of these data. It says briefly explain your choices, so I'll write this out as for the center, use M since these data are skewed. So that's a statistic we would use for the center. It didn't ask us to actually calculate that statistic. That's kind of uncomfortable. I would probably do that anyway. I mean, you can't lose points for just adding extra information. So if that bothers you, go ahead and calculate it right here. The median value from RStudio. Oh, sorry, my windows don't go that way so easily. Came out at 862.5. So next, we want the right statistic to represent the spread of the data. But here's a quick way to answer this one. For the spread, use IQR. You could say because the data are skewed, but there's a larger reason. Our statistics are paired. If you're using the sample mean, you must use the sample standard deviation. But if you're using the median, you must use the interquartile range. So a great way to answer this one is to say, use the interquartile range since we used M for the center. Then what we want to do next is calculate that interquartile range. I mean, it's optional. The problem didn't tell you to do that, but we'll probably do that in the notes here just so that we have a value, gets us that extra practice. We'll be able to do it right now. We're on our last minute. But here's how the notes will go for today. We'll come back to right here, finish out part C, calculate that interquartile range, and then put in this big summary problem here with some graphics and such. And that means for this assignment, I need to push the due date because the pattern I want to get into is the moment we finish the chapter in its entirety, we'll have a 1-week turnaround on the due date for this. So I'll push the due date back to when we come back on Monday's class, finish this off, will be due the Monday after. Well, any last questions, folks, then, before we call it a night? Okay, well, have a wonderful weekend, everyone. Kind of weird, only working one day of the week. But if you have questions, don't hesitate to reach out, and I'll be very happy to help out. Thanks, Olivia. Thanks, folks. And it's kind of weird to say happy weekend on a Wednesday, but I know people probably still have an entire work week to get through, but hey, for as long as this class is concerned, happy weekend. Oh, yeah.